Thank you everyone for joining us today. We're going to go ahead and get started with today's generator sizing webinar. With us today, we have Amy Thompson from Generac, who's going to be presenting. A couple quick notes before we start. We do have at the bottom of your page a question and answer section. Feel free to submit questions at any point during the presentation. We'll gather those and save those for a question and answer at the end. If you have any issues, you can also chat with us or raise your hand. We can take care of any audio issues or other questions you have throughout. This presentation is available for CEU and PDH credits. I'll send out information on the chat, as well as a document on how you can register for those. Like I said, if you have any questions, feel free to send them to us, and we will send out a recording of this at a later date. For now, we'll just turn it over to Amy.
Perfect. Okay. Good day to everyone, and I'd like to thank you all for joining us for this webinar today. As Tyler mentioned, my name is Amy Thompson. I am a Power Solutions Manager for Generac, and I cover a large part of the Western U.S., including your territory. I've been with Generac for about 1.5 years. I hope to work with all of you in the near future. So let's go ahead and jump on into the topic of the day, generator sizing. This topic, just for a note, has had to be broken down into 2 modules because of the many things that you need to consider when sizing a generator for different projects. And due to time constraints, we're only going to be able to get to the first module today, but we can schedule another session to go over the second part of the presentation at a later date. And we can also jump into showing you examples of how to use our Power Design Pro, which is our sizing program. We can give real world examples and show you how to go through using that software. So that's just FYI for a later date. So now for the first slide, we're going to talk just a little bit of background on Generac. We won't go too deep into it, but just want to give you a little bit of information on us as the second largest generator manufacturer in North America. We also are the largest manufacturer of natural gas power generator sets in North America. I think most of you are familiar with our residential side. We're probably most known for that, but we also do have an industrial/commercial side, which is the side of the company that I represent. We invest heavily in research and development and have about 27 test cells that's dedicated strictly to development. Our brand does extend far beyond just generators. Even we have other products as well in our portfolio. So when you think about Generac, you may think about generators only, but we do have a full widespread of other offerings from our company as well. We have 6 plants in Wisconsin and many others around the world with about, I guess, more than 9,500 employees currently. Let's move on into the topic. Our agenda for this module is to go over various sizing approaches to sizing a project, sizing for new construction and the associated challenges that may come along, and how to go about sizing for some additional and unexpected surprises. You can really approach sizing from 2 different viewpoints, being a whole building with all loads starting and operating at the same time, or you can approach it looking at individual loads. During this presentation, we're going to get into some of the NEC requirements that we need to remember when doing a sizing. We're also going to discuss some of the design rules of thumb that some engineers use sometimes, like how much kilowatt per square foot would be needed in order to calculate what size utility service or backup service you're going to need to power your building or your application. When you're looking at an existing facility, it's easy to size your generator based on measurement data, like let's just say if you go over a year's worth of utility bills and discover what the largest peak demand is for that year and size from that measurement data. You can also use as I mentioned before, our sizing program, Power Design Pro, which you can use to size based on individual loads, typically making sure that you apply the largest load from the building to make sure that the voltage and the frequency dips stay within acceptable limits. Traditionally, when sizing emergency systems, you would assume that all loads would start up and run at the same time and size your generator using that assumption. Well, this works if we're talking about an emergency system that will only be powering things like egress or exit lighting. But when you're trying to size for like things like hospital emergency systems, you kind of run a risk of oversizing that generator using that method, because if you're assuming that all loads will be running at the same time during an emergency situation, that's generally not the case. Hospitals have different sizing requirements. They are sized per Article 220, which covers branch and feeder circuit sizing. This applies certain load factors to certain load types. And in healthcare, you want to only size the generator to cover the maximum actual demand that's likely to be produced during an emergency situation, such as, powering your operating rooms or your life safety or your life support systems. By doing this, you'll likely avoid having the generator be so lightly loaded that you run the risk of wet stacking due to oversizing, which of course brings its own set of problems when that happens. Here, we're just going to take note of some changes to the NEC regulation for sizing legally required standby from the 2017 NEC to the 2020 NEC. And of course, depending on your county, you should know which NEC your AHJ is currently adopted. Basically, the 2020 NEC makes Article 220 the standard for all load types, be it emergency, legally required, or even optional standby. So if your region has accepted the 2020 code, then you will no longer consider all loads operating at the same time, but rather size for the most likely maximum demand produced at any given time. So now Article 220 is now the main sizing method that's recognized by the National Electric Code. And we're going to talk about parts 3 and 4 here. Part 3 is where you are adding up the load totals on different branch circuits and using whatever applicable load factors there are based on types of loads, of the type of loads that are connected. This is also where you want to consider any loads that would not be used simultaneously, things like cooling and your heating loads. So in the case of non-coincidental loads, you have to be sure to calculate using the larger load only, meaning if your heating system is rated at about 100 BTU and your cooling system is rated at, let's just say 150 BTU, then you're going to size to make sure that the generator that you have is going to be able to cover that 150 BTU, which is the larger load. You just want to make sure that you are not sizing as if both systems are going to be running simultaneously, because obviously you're not going to be running your heat during the summer and your AC in the winter. So part 4 goes into dealing with existing facilities. In these instances, we can determine our sizing needs based on 2 factors. Utility bills, which show peak demand data over a full year, or power analysis, whereby there's data collected by a power data logger over a 30-day period or so. When you're using these methods, you want to be sure to make sure that you calculate about 80% of peak demand for your generator sizing. So that would basically be using the largest peak demand and multiplying that by 1.25 to get your generator size. So for an existing facility, a billing history is a very good way to capture peak load levels. For example, with unique load characteristics, things like transients and harmonics, a power analyzer can capture key information that's needed to size the generator. Commercial and industrial customers are typically charged for electricity in 2 ways. That would be peak demand, or peak kW for that month, and energy used, which is on the bill and appears as kilowatt hours. The peak demand on the bill is the information that we are interested in. You'll need to use a whole year, not just 1 month, but you'll want to look at a full year of your billing history to make sure that you're capturing seasonal load effects. The peak demand is based on a moving 15-minute average So it doesn't capture momentary load transients during peak loads, like starting a motor. If the application, it has a large motor that cycles on and off during peak load periods, then that motor starting transient needs to be added to the peak demand on the utility bill. And for across the line motor starting, you'll add horsepower as an incremental kW load. And we're going to talk about motor starting and sizing and rules of thumbs and things like that a little bit later. This is just a high level discussion. So we've been discussing Article 220, but you'll notice that in the code, they also have the words other approved methods in there, and that gives the engineer some flexibility. What this means is that most of the time, an AHJ will give engineers some leeway beyond the NEC code if there's a PE stamp on those drawings, because that PE stamp goes a long way to giving the AHJ confidence that the engineers do have or have done their due diligence and are working within given guidelines. Some flexibilities that engineers may exercise are using things like historical design rules or adding in certain factors for uncertainty or future load growth. Let's get into some more engineering judgment. Okay, so we can break sizing down into two categories. One being taking a whole building and all of its loads, adding them up to total the KW or your peak KW based on your utility history, and then coming up with a generator size based on that information. You'll also want to look for the largest loads that need to be started, say motor loads, so that we can analyze the transients and the harmonics from those loads. The second way to look at sizing is looking at different unique characteristics of a particular load, such as soft starters or VFDs. This is something that is covered more in the second module that we can hopefully do at a future date with you all. So back to the whole building. The great thing about Power Design Pro, which is Generac's sizing tool, is that you can take the peak demand from the utility bills or power analysis tool and then enter that into Power Design Pro. When you're doing that, though, it's best if there is more than one machine creating that load. So you're generally not going to have one piece of equipment that's requiring, let's just say, 1,000 kilowatts of peak demand. So in that case, what you want to look at doing is, if you're only going from information that you're getting from the power analysis tool or from utility bills, it's best to try to break that total KW down into a couple of different items and put them in a group. So if you have 100 or if you have 1,000 kW peak demand, maybe breaking that down into 10 of 100 kW lines and putting those in a group to see how that affects the generator sizing. This will give the program the ability to view that demand more realistically and not looking as if all loads are simultaneously running and coming on at the same time in a single step. And if you do have a large load, such as an across the line motor, then you'll want to enter that in as a separate line so that you can see the effects that starting that particular motor, the large motor, will have on the generator, like a voltage dip and ensure that you have enough capacity to handle starting that motor with all the other loads that are also in the that you're using to size for. Most sizing programs are optimized to view and analyze a few discrete loads. You don't really want to try to input every single one of the hundreds of loads that possibly is in a building into the sizing tool when you're sizing for a generator. Because when you do that, the program will probably assume that each of those loads will be running at the same time, meaning that even if they don't all start simultaneously, most sizing tools will figure that all the loads will be running at the same time and drawing power at the same time. And as we know, more times than not, you're not really going to be using all loads in the building at the same time. Let's think about it like it's your house. You're probably not in the kitchen cooking with the oven and using the microwave and the blender and your massage chair and your adjustable bed and your blow dryer, all of that at the same time. you don't want to size your generator based on everything being on at the same time. If you did that, then you would need a much larger generator than the standard, let's say 20 kW that's usually put on a house. So you want to focus on the discrete loads, such as in the case of a pump station, if you have 3 pumps, then you'll size for those because you can power those. You can generally power the other minimal loads with the generator that's needed to power those pumps as well. The sizing program also does a good job capturing and analyzing harmonics for distorting loads. You'll want to capture the number of VFDs used in a building to make sure that the harmonics aren't too much for the generator. And that software that we've been talking about, Power Design Pro, can really help with mechanical designs, meaning it will help you show options for gas piping, exhaust piping, and even help with layout, meaning you can sort of put the generators in this layout tool and to show you what kind of footprint you will need for the number of units that you will be using. Power Design Pro has a couple of different ways to enter your loads. You can enter them in groups and you can enter them in steps. When you use groups, you're assuming that the loads are non-concurrently starting, meaning that all loads in that group are not going to come on at once, which is referred to as natural sequencing. Steps assumes that all loads will be started concurrently or at the same time. And most manufacturers' sizing tools only use steps as sequencing methods, but we feel at Generac that groups captures more of the reality of how building loads actually work. Some people may not like that because they feel like they need to be able to sequence the loads. But when you really look at the loads in most applications, they don't use active sequencing, but instead they use natural sequencing. And if you think about it, generally when your utility fails, you will notice that not everything comes back up at the same time, except maybe lighting. So you'll want to consider that when modeling your sequencing in whatever sizing tool you choose. Now, I do say that we prefer to use grouping, but in our sizing tool, we do have the ability to use steps as well. So you can still do your sizing how you think is necessary for that particular project. New construction sizing relies a lot on engineering judgment. It should also involve the end user's input because they can give you basically a relative scope of supply. They will know what they have to have powered on if there's a utility outage situation and what can remain off until that utility is restored. As the end user decides which loads are essential and which loads are optional, then they may need some engineering help to kind of fine tune the generator scope of supply and determine which operational expectations may offer some cost saving. Things that an engineer takes into account when sizing for new construction are things like, how will the loads be separated? Are we backing up the entire building or just certain portions? What type of loads are connected? And at the same time, keeping in mind that motor loads generally cause the most variance in generator sizing. So sizing a generator is not limited to the existing loads, but also you have to take into account if there are going to be any future loads that are going to be added. Historically, this is done by installing a larger generator if they think that they're going to expand their operations in the near future. They would have previously just added a large generator with the anticipation of how much they think they will be adding in the future. But this can cause some negative results like poor use of initial capital and possibly wet stacking because it's too large for the current load responsibility that is over the load that is currently on the generator. And you don't want to do that because it could cause more issues, and you would have to buy. You may end up having to replace that when you go to extend your operations. So things that you want to think about when considering load growth are how often will you be adding additional loads? Is it going to be every year? Are you going to add every 5 years, maybe even every 10 years? Are we fairly certain that this is going to come to fruition? So are you sure that you're definitely going to be adding loads in the future? And can this end user possibly benefit from expandable or parallelable options, which you can see as an example in the slide here. So generally, when powering an entire facility, there is not going to be one load that tends to be significant enough to cause any serious issues. You should always think of the generator as a limited source that's going to experience voltage and frequency variations in response to large load steps. The effect of starting the largest cyclical load should be evaluated with respect to the system's voltage dip. Voltage dips generally that are larger than 15% are kind of unacceptable for non-dedicated loads or loads that could reset on the transient. So you want to keep that in mind and make sure that you are mindful of your voltage dips. Generators are rated for a limited power factor range, generally between 0.8 power factor and 1 power factor when the current is lagging the voltage. Leading the voltage happens when the current leads the voltage, which is usually caused by capacitive loads like power factor correction capacitors or things like capacitors within the harmonic filters. A leading power factor can cause things like voltage instability or overvoltage shutdowns. And this isn't something that happens often, but when it does, you really only have a couple of options to deal with it. You'll either need to add some type of other lagging power factor loads to the system, or just remove or shut down the power factor elements. Now we're going to get into motor starting. All generators are made up of 2 machines, and I think all of us here probably pretty clear on those two machines. The first one is the alternator, and it is the power converter and is responsible for the voltage control. Then there's the engine, excuse me, that is the source of power, and it's responsible for frequency control. The alternator can sometimes be upsized a few kWs, maybe 1 or 2 steps in comparison to the engine. And that can help you when you're dealing with large motors and need to minimize voltage dips during those motor starts. Keep in mind that when you do upsize the alternator, that is not going to increase the kilowatt output by that engine. You're just doing that in order to be able to maintain or to modify your voltage dips when those motors come in. Here in this graph, we can see that the SKVA requirements for a typical across the line motor start. When starting motors, excuse me, they typically require about 6 times the kVA to start them than they need to run. And that's illustrated here, as you can see on the left side of this graph, in the percent current for full load. The duration that the generator needs to support the increased SKVA is a function of motor speed and not time. So if the motor takes a long time to accelerate, then the generator has to carry that load longer. The SKVA value stays fairly high until the motor is almost at rated speed. And then the alternator needs to be large enough, to be able to handle a SKVA spike and maintain enough voltage stiffness to keep our system up and running and supporting all the loads. At a startup for a motor, it draws an immediate rush of current, which we call inrush. And as we'll see, that is typically that multiplier of 6 that we've been talking about. This current is often referred to as lock rotor current, or LRA, because this is the same current that's drawn, this is the same current draw that would occur if the motor's rotors were locked. Since a generator's current capability varies depending on the voltage, we don't specify the alternator's transient capability in terms of amps, but instead we use the term SKVA, or starting kVA. For a given excitation level, the SKVA is dependent on output voltage. And we can convert LRA, to SKVA by simply multiplying that voltage times the current times the square root of the number of phases, in this case 3, and then dividing by 1,000. So you'll see here in this example, the 750 amps, which is basically a typical 100 horsepower motor, starting at 480 volts with 3 phases, and it's going to require, after you divide that by 1,000, you'll see that it requires about 623 starting kVA to start that motor. Motor nameplates, I think you know how to look at the motor nameplates on a motor. It gives you the NEMA starting code on those plates, and based on that code, we can determine what the SKVA will be. In the industrial market, we see a lot of code G motors. So if you look at the motor starting table here on the right, you can see that it gives a range for those motors of 5.6 to 6.3 SKVA per horsepower. So we generally use the mid-range of that value for the G code motor and go with 6 in our examples and for our rules of thumb. And let's look at this example here. It's using a typical 100 horsepower motor. We're assuming a typical G code motor, and the SKVA is 6 times its horsepower. So you can see that it's 600 SKVA. We do need to recognize, as we're talking here though about these motors and these starting codes, that you will not always have a G code motor. You can run across some other NEMA starting codes. So we need to be mindful that we're making sure to use the correct multiplier based on the actual motor that is in that application. When we start looking for the SKVA, as we just went over, the motor nameplate will provide you what you need to do that calculation. Or you can use LRA, locked rotor current, times the voltage to get the SKVA. Now, sometimes you'll notice that when you're getting your information from the end user or whomever it is you're getting your information from, they can sometimes give you misinformation. So it's a good thing to do, or it's a good thing to validate what they're telling you by using the equations that we've talked about, or using your rule of thumb to see if the SKVA looks right for that particular horsepower. And if it doesn't look right, then you should go back and question the data that you were given. Also, if anyone ever gives you a nameplate codes of B, C, or D, or anything like that, you'll want to make sure that they take a quick look and make sure and give you the proper code, because in starting codes are generally not that low. We need a starting code that reflects either an F or something higher. Let's jump into this real quick, where we're talking about one specific manufacturer expressing their motor starting based on 90% sustained. It's actually a voltage dip of 40 to 50%. This is well beyond the 35% voltage dip limit of the NEMA motor starter. When an alternator experiences a motor start, or SKVA, then a voltage dip will occur. And the larger the motor is, the greater the voltage dip is that you're going to get. Each line on this graph here, I can't find my pointer, sorry guys. Each line on this graph represents the alternator's response characteristics to starting larger motors. And if you'll notice that for all of the lines except for C, the voltage returns to 100% voltage. Line C represents a certain OEM that uses quote unquote 90% sustained SKVA. That term, sustained, actually is the recovery voltage. And the alternator, the alternator has been given such a large kVA load step that it has a 40 to 50% voltage dip and can only recover to about 90% of the rated voltage. And this is an extreme limit of the alternator's capability. In our industry, we limit our voltage dips to 35, and this corresponds to the maximum voltage dip allowed by the NEMA motor starter. Some engineers mistakenly think that 90% sustain means only a 10% voltage dip, and that's just not correct. This graph illustrates why, as an industry, we limit our maximum SKVA data to 35% voltage dip. As you extend beyond that 35% voltage dip, you'll notice that the alternator's voltage reaches a collapse point. The 90% sustain data point is at the point of voltage collapse. And with this level of SKVA, the alternator's voltage regulator, the voltage regulator for the alternator is completely on, the exciter is completely on, the main rotor is completely on, and the output voltage has only recovered still to the 90% of the rated voltage. So why does an alternator have a voltage dip? This graph will show that the motor drawing locked rotor current, and when this current flows through the source impedance of the alternator, a resulting voltage dip occurs. Let's remember Ohm's law is voltage is equal to current times resistance. So when a current is passed through a resistance or an impedance, a voltage drop occurs across that resistance. Let's think of it like pinching a water hose. When the water current flowing through that hose's restriction point, it will experience a pressure drop across that restriction. So then how do we minimize the voltage dip? Since voltage dip equals locked rotor current times transient reactance, we only have two choices. We either need to limit the LRA or reduce the alternator subtransient reactance. And upsizing alternator effectively reduces that subtransient reactance. And that's why larger alternators experience lower voltage dips as well. This slide shows us the effect of upsizing your alternator to reduce those voltage dips. So for this example, a 50 horsepower motor drawing 300 SKVA with a standard 130 kW alternator would have a 35% voltage dip. And if you slide over that, slide across that graph or that chart, you'll see that with the larger alternator, your voltage dip reduces. So if you're trying to get to that 15% threshold for things like a fire pump or things like that, you'll need to upsize your alternator to about 300 kW as shown here. So since we've talked about the alternator and voltage dips, let's turn to the engine and the effects that starting a large motor can have on an engine. Remember that when we talked about the components of a generator, we noted that the engine is responsible for frequency control. So when starting a large motor, the engine is hit with a large starting kW, which creates a frequency dip. The amount of the frequency dip will vary engine to engine based on that engine's design parameters, such as the injection system or turbo boost, genset inertia, etc. For example, a diesel engine will have less of a dip than a gas unit. So what aspect of kVA actually causes the engine to be loaded? Excuse me. When an electric motor starts, it draws a huge surge of current or LRA. So we generally take the LRA, and calculate a kVA with that. But we need a way to calculate kilowatts because that's what the engine sees. So to do that, we use a power factor to take us from kVA to kilowatts. And the power factor is the ratio of kilowatt to kVA, which helps us to calculate starting kVA. So for an electric engine, 0.3 is a good rule of thumb for the power factor during a startup. And so if we have an engine with 600 starting kVA, we multiply that by the starting factor of 0.3, and we see that we have a 180 starting kilowatt for this particular engine. When we look at frequency dip, we can sort of deduce that a good rule of thumb for determining starting kW is 2 times the horsepower of the motor that we're starting. if we're only starting one motor. This may be a little conservative, but it's a great tool to help a customer look at what he needs to consider when determining the size of his generator. So if he has a 50 horsepower motor, then he will need to make sure that the generator has a minimum of 100 kilowatts free capacity. The amount of the frequency dip does vary from engine to engine, as we talked about before, based on the parameters of that engine. There is a feature called volts per hertz in the generator controller that's going to allow us to shed some load to help the engine recover from frequency dips by keeping the output voltage of the alternator low. 10 hertz is about average. Understand that most equipment is not super sensitive to frequency dips unless we're talking about things like certain UPS technologies. Rules of thumb are handy, helping us to double check data quickly. We have seen that in an alternator, starting kVA is relatively equal to about 6 times the horsepower of the motor. And for the engine, starting kW is equal to about 2 times the horsepower of the motor. For calculating running data, we also have rules of thumb, such as the fact that motors usually run at about 1 times the kVA. So if you have a 10 horsepower motor, you can assume that it's drawing 10 kVA from the alternator while running. And for the engine, motors tend to run at about 0.85 power factor. These rules of thumb cannot be applied to specialty motors. So just remember that things like submersibles and submersible well pumps, but just remember that this is still a good way to do some quick math when dealing with standard motors. Given the rules of thumbs that we just talked about, let's go over a couple of exercises, okay? We're going to talk about a pump station project where there's 3 pumps, a 50 horsepower, a 100 horsepower, and a 200 horsepower motor. We're going to see through several scenarios which gives us the smallest generator and which scenario is going to show us, or which scenario is going to give us the most likely real world situation and produce that and see what size generator that produces. So the first scenario we're going to talk about is going to look at starting the largest motor first, or largest pump first, which is the 200 horsepower motor, and then going in descending order. What we're going to find when we do this is that sizing in this order is going to give us the smallest generator, because starting the larger pump first will give the largest hit on the generator first and provide the most capacity left for the other loads. Reversing that order, starting the 50 horsepower motor first, which is the smallest one, and then going in ascending order will require a larger generator, because we lose some genset capacity if the 200 horsepower is being started after the other motors are already on. This is the more realistic or real world scenario, because on a real pump station, or for motors in general, I should say, they tend to cycle on and off and don't always come on in the same sequence. So that, again, is the more realistic or real world scenario. The last scenario we're going to look at is going to be having all the motors start at one time simultaneously, which doesn't generally happen because of natural sequencing. There's a thin possibility this might happen, in which case the end user needs to be able to tell you that this is going to happen, even if it doesn't happen every single time. We need to know that that is something, that is a scenario that could possibly happen and size accordingly. And if it's something that the end user is concerned about, then we can always add relays to prevent that from happening, unless it's necessary, again, for that sequence of their operations. So let's jump into the first scenario. So in the first scenario, using the rules of thumb, we know that in order to start the 200 horsepower motor, we're going to multiply the horsepower times 2. And that's going to require 200 kilowatt to start the motor. We then multiply 200 times 0.85 and see that we need 170 kilowatts to keep that motor running. The 170 kilowatts becomes a preload on the generator when the next motor starts. So the next motor is the 100 horsepower motor, which requires 200 kilowatt to start. And then we add that to the 100 kilowatt of the preload. And when we look at the original 400 kilowatt we see needed to start the 200 horsepower motor, we see that the generator size from the first load step will be large enough to start the second motor also. So now we have 300 horsepower running for the two motors, which results in 255 kilowatt of preload on the generator, okay? Then the third motor starts, which is the 50 horsepower and requires 100 kilowatts, which adds to the 255 kilowatt of preload. Based on these calculations, we can determine that with this sequence, the 400 kilowatt generator has enough capacity to start and run all three motors. Next, we will need to determine the alternator requirements to support the voltage dip of that application. And to calculate that voltage dip, we remember that the SKVA is equal to 6 times the horsepower of the largest motor that is being started, which will give you 1200 SKVA, 6 times 200 horsepower. Using the SKVA from the alternator data sheets that we have, we see that the 500 kilowatt alternator has a voltage dip of about 34%. And then we remember that our limit of a voltage dip is 35% based on the NEMA motor starting requirements. So that's that scenario. Let's go to example 2. In example 2, we will be starting the motors in ascending order. And as we previously discussed, since the motors will be going on and off or cycling, this scenario is the most real world example, okay? So the preload in this example from the first two motors is 127 kilowatts. Then we start the 200 horsepower motor, which produces 400 starting kilowatts power draw, and add that to the 127 kilowatt preload. You will see that now we have a peak of 527 kilowatt to start those motors in this scenario. So we would assume that we would need a generator somewhere between 500 and 600 kW for this particular scenario. We could probably get away with 500 kilowatts just because our multiplier of 2 is a bit of a conservative and gives us a little bit of a buffer. Now for the last scenario, we will be assuming that all three motors are start at the same time or concurrently. So we take the sum of all three of those motors and multiply that by 2 and come up with 700 kW. Again, this isn't really a true depiction of how most motor sequencing is in the real world, but we just want to make sure that you see the differences between all three scenarios. But more than likely, we will not be sizing our generators this way. Unless there is, let's say, a plant that uses certain processes in which there is a specific sequence that a group of motors needs to be started at the same time for a certain process to work. Then you would need to use a single step for all of the motors. Otherwise, natural sequencing is generally how motor loads work. So in summary, for an existing building, we can use utility billing history for peak demand and power measurements to calculate your required generator size. Remember to find out the largest transient load in that particular building in order to be as accurate as possible. Then you would enter your building preload into your Power Design Pro, our software, or whatever software you're using, and make sure to subtract the running kW from the largest load from the preload and add that in separately into the program. That way you can see the effects of the voltage dip from the large load. For new construction, we discussed how engineering judgment and design rules play a role. We also discussed how scalability for NPS or parallel systems is a great value prop for the ability to grow, especially in cases with a lot of uncertainty about the future. We then talked briefly about leading power factor, which is rare, but if it does happen, you can just turn off the power factor correction or add some offsetting lagging loads. And lastly, we went into some sizing examples where we used our rules of thumb that we discussed to size different scenarios and talked about real world sizing versus sizing to find the smallest generator, which is rarely the best way to do sizing. So that basically covers the topic at hand for the first module. And I want to thank everybody for joining us today. If you have any questions, we can address those now.
Great. Thank you, Amy. We did have a couple questions come in, but feel free to submit more questions as we go. The first question we had actually brought up two different situations. They asked about what would differ on sizing if you were sizing for a fire pump, and also if you were sizing for a smaller building like a garage or something similar to that. Are there any differing considerations?
The biggest thing on the fire pump is that you want to make sure you're maintaining a 15% or lower voltage dip. You can't go above 15% on the voltage dip for your fire pumps. That is the biggest consideration when you're doing that sizing. As far as a garage or any other standard building, you would basically, if you're looking at a garage door, that would be considered like a motor. So you would size based on using it as a motor. In general, those would be the biggest factors, especially for a fire pump.
Okay.
Go ahead.
All right. We did have another question come in. You mentioned wet stacking. What is wet stacking?
Wet stacking is when you have your generator is too lightly loaded and it results in a buildup of oil and film on the generator, which can cause the generator to fail eventually if it's not repaired. And that is when you're under, I would say, 30% load. So you want to make sure that when you're doing a sizing, you are staying above that 30% threshold to try to minimize any issues with wet stacking.
Great.
That makes sense?
It does. We have another question. Would there be any differing sizing considerations if your generator is primarily going to be used for peak demand shaving?
Yes, there are. John, are you on?
Yep, I'm here. I was on mute. Sorry.
This is one I want you to take just to do
Sure.
a little more thorough on that.
Yeah. So one of the things you do want to keep in mind is that so we start talking about sizing a generator for standby application versus sizing a generator for peak demand or for a peak shaving or demand response type of application. Is a standby generator, you have to make sure that it's certified for standby use from an emission standpoint. That's a whole different conversation we can have. But from a sizing standpoint, we're expecting to see a load factor somewhere in the neighborhood of about a 75, no more than 80% average load factor with a fluctuation, right? So sometimes it may be running 50% load, sometimes it may be running 90% load, expecting that type of a fluctuation. In a demand response or peak shaving type application, we still expect to see a fluctuating load, but we only want to see a load average, not in the 75 to 80% range, but somewhere in probably the 70% range, only because you're adding additional hours to it. Just like anything else, the enemy of a long-term care of a piece of equipment is how hot it gets. The more load you put on it, the hotter it's going to get. So if you're applying a generator in a peak shaving application versus a standby, you may be a bit more conservative in the sizing of the generator, simply because you're going to be putting more hours on the piece of equipment. So your average load factor, instead of being 75, maybe 80%, we're going to put an average load factor of somewhere around 70%.
Great. Thank you. There was a question. You mentioned generator paralleling and planning for future growth. What considerations do you need to take into account if you're paralleling generators as far as sizing?
If you know that you're going to be expanding, there's a couple of different things when you're doing a parallel system that come into play, such as, are you looking for redundancy? Are you looking to be able to once you expand, are you keeping in mind how much real estate you have when you're looking into the future, to make sure that you're sizing based on the space that you have, basically. Our generators right now are all capable of doing onboard paralleling. So that's something that you also keep in mind, because that eliminates a large portion of capital if you're able to eliminate I just forgot the word. What's the word I'm looking for?
I'll jump in here, just a quick help. A couple of things this made me brought in, right? One, make sure that you've got the space for the generation. And also kind of check, customers talk about expanding. How strong is their business plan? I know that's not usually a conversation you would have as an engineer, but if they say, hey, we're going to be ready to expand this facility in 5 years, we're talking about a parallel solution. Is their business plan really going to get them there? Right. Another thing is looking at it strictly from a distribution standpoint. You need to put the distribution in place today.
Yeah.
Even if you're going to expand and add more generators later, you want to make sure you put all the distribution in place now. So all you're doing is adding generation to the system. It's more of a plug and play system, as Amy mentioned, right? The generators are already ready to parallel. It's just dropping a unit down, tying it with the others, and it'll sink in and do its thing. But if you've got to start adding additional distribution or beefing it up because you only put 2,000 amp panel or distribution, you need 3,000 amp or whatever the size is. Now you got to shut the whole place down. All right. So you make sure that you're planning the distribution for expansion, even if you're not adding the generation until later.
Great. We had a question come in about derating. It's two parts here. The first part is, does Power Design Pro handle derates for altitude and temperature if entered in? And the second part is, if you're not using Power Design Pro, how do you manually derate for altitude and temperature?
So yes, Power Design Pro will allow you to input things such as your altitude and your ambient temperature and things of that nature. And it will take those factors into consideration when outputting the recommended generator size. If you don't have Power Design Pro, we do have a document that will show you how each generator will derate. So it will give you a percentage that you would be able to subtract from the output of the generator to determine exactly at that elevation that you're using it at, what that output for the generator will be.
Great. Are there other common factors that may require derating other than altitude and temperature?
Not that I can think of, John.
Well, you always want to make sure, all of the conversations that we have regarding this, make sure that you have a good quality fuel. So, if you're using pipeline natural gas, there's the assumption that you are using 1,000 BTU fuel. But if you know that this particular natural gas provider has got some issues with their fuel quality, that's a conversation to have. If you are not maintaining your diesel fuel, if we switch into diesel fuel, if you're not taking care of your diesel fuel, there's a potential that the unit's not going to perform as well, right? The longer that you hold that diesel fuel in that tank, it's going to chemically break down. It may not give you the BTUs that you're expecting. Also, in some of the higher altitude or some of the colder environments, people will blend their diesel fuel with kerosene, right, to get a lower freezing point or cloud point within that fuel. And when you do that, you're also using a fuel that does not have the BTUs of diesel. And so you would be derating that fuel by maybe up to 5%. I know that's what happens in the colder climates is during the year, they have heating oil, and that heating oil they use as the kerosene. They cut the diesel with the kerosene, and they're going to lose the potency because it's not as quite a powerful fuel. So those are a couple other things to think about is what are the what fuel are you using, and making sure that it's a good quality fuel that's going to give you the output that you're looking for.
That's a good point.
Great. Thank you. All right. Well, that looks like all the questions that we've had come in today. So again, we want to thank Amy and John for joining us for today's webinar, and thank them for the information they shared. And we look forward to seeing you in the next webinar.
Thanks so much, everyone.
Thank you. Thanks for participating.